Good afternoon, everyone. So today I'll be talking about optimal sequencing policies for recovery of systems deteriorating after disasters. Disasters are non-routine events that have the potential to cause catastrophic impacts. And usually these events cause significant damage to infrastructure systems like power, transportation, etc. For instance, thousands of roads were closed during Hurricane Michael and millions of people were left out of power after Hurricane Irma. And it is important to focus on the recovery of infrastructure systems after such events because it influences the return of displaced communities. And it also affects the functionality of emergency services like the movement of ambulances, recovery agencies, and so on. So in this work, we focus on a scenario where infrastructure components deteriorate after a disaster unless they are being repaired. And that is relevant because roads and pipelines face accelerated damage after floods due to water and corrosion. And therefore, we consider two threshold states for these components after disasters. The first threshold state is the permanent failure state, which is state at which a component deteriorates to such a level that it either requires full replacement or repair, which is usually expensive and thus undesirable. The other threshold state is the permanent repair state, which is state at which the health value of this component is brought back to the full level and it is not further affected by any deterioration processes. So the key question which is of our interest is what control sequence should be followed for repairing these different infrastructure components in order to maximize the number of components that are permanently repaired. This problem is also relevant for other applications. For instance, in the protection of cyber physical systems, there can be multiple servers that are partially damaged by a virus or a hacker. And in that event, there might be a limited amount of time before these servers become fully compromised. And in the event when there is shortage of resources and manpower available for protecting these systems, then optimal decisions would have to be made on which servers should be first protected, and so on. Similarly, in the firefighting scenarios, the aim of the firefighters is to ensure that fires do not reach the state of flashover, which is a state at which everything starts to burn very rapidly, and there is very less hope of recovering anything that is there. And therefore, under the event, when there is some shortage on the resources for firefighting, and there are multiple fires simultaneously, then optimal decisions would have to be made by these firefighters to ensure that least damage occurs. And in all of these applications, we see that these components have two kind of thresholds. One is a desirable threshold, which I refer to as the permanent repair state, and the other is the undesirable threshold, which I refer to as the permanent failure state. And the objective of the recovery agencies is to ensure that largest number of components reach the desirable threshold without reaching this undesirable threshold. So I'll briefly go over through the existing literature before presenting my results. So there are several works in disaster recovery that are focused on the repair of infrastructure systems, but most of these works model do not consider deterioration processes, and many of these studies are specific to some specific infrastructure networks, which is not the case in our problem. And therefore, the results that are provided in these works differ from the results that we provide. Similarly, our problem comes in the general class of optimal control switch systems, because in a switch system, there are multiple subsystems and only one subsystem can control at each time step, which is analogous to our problem, because if there is a single repair agency, then at most one component can be targeted at each time step. However, there are no results of framework to characterize optimal policies for all the classes of problems in this area of switch systems. And therefore, this remains an active area of research. Similarly, our problem has high-level analogies to scheduling of thermostatically controlled loads, job scheduling, machine repair, queued systems, and so on. However, there are differences either in terms of the objective functions that are considered in these works, or in some of these studies, there is no notion of permanent failure or no notion of permanent repair, and so on. And therefore, the optimal policies that are characterized in these works differ from the policies that we provide. And our contributions is that we are focusing on these deteriorating components that fail if they are not repaired in time. And we characterize optimal and near optimal feedback policies for maximizing recovery under various scenarios. So now I'll formally describe this problem. There are n components that are referred to as nodes belonging to the set V. And in a disaster scenario, a node could represent a section of a road network or a portion of a gas network, etc. And there is an agency or an entity that seeks to repair these nodes. The health value of a node j at time step t is denoted by VJT, and it lies in the interval 0 to 1. And this interval could have been any bounded interval, but without loss of generality, we take it to be 0 to 1, where 0 represents the permanent failure state and 1 represents the permanent repair state. And the control action which is taken by the entity at time step t is denoted by ut, and it represents the node that is targeted by the entity at this time step. So now I'll provide some illustrations to show the dynamics of this problem. So if the health value of a node j at time step t is 1, that is, it is in the permanent repair state, then it remains the same in the next time step also. If the health value of a node j at time step t is 0, that is, it is in the permanent failure state, then it remains the same in the next time step also. However, if the health value of a node j at time step t lies between 0 and 1, and this node is targeted by the entity at this time step, then its health value increases by an amount delta increase. Otherwise, it decreases by an amount delta decrease. And I also define the concept of a jump that I'll use later. So the entity is said to have made a jump at time step t if the entity starts targeting a different node at this time step before permanently repairing the node it targeted in the last time step. And therefore, a non-jumping sequence is a sequence that does not contain any jumps. And our objective is to characterize a sequence that maximizes the total number of nodes that are permanently repaired. So to give an example of a problem, consider the scenario where we have three nodes, A, B, and C, with initial health values equal to 0.8, 0.6, and 0.4 respectively. And the deterioration and the repair rates are both equal to 0.2. So the question here is, what is the optimal control sequence? Should we first target node A, which is the healthiest node, or should we first target node C, which is the least healthy node? So I'll come back to the answer of this question again in my presentation. So now I'll start to present my results. I divide my analysis into two parts. I first consider the case when the deterioration rate is larger than or equal to the repair rate, and then I consider the other case. So suppose that the deterioration rate is larger than or equal to the repair rate, then non-jumping sequences are optimal. So that means that if a node targets if an entity targets a node, then it should permanently repair it before it targets any other node. And to give an idea of the proof of this result, we first considered an arbitrary sequence that has at least one jump, and suppose it permanently repairs X nodes. Then we argued that it is possible to come up with a sequence that has one less jump than the given sequence, and that also permanently repairs X nodes. And then we can iteratively use this result to come up with a sequence that does not contain any jumps, and that will also permanently repair X nodes. And then thus the result follows. Now, before presenting the next result, I present a set of regularity assumptions that ensure that each node is permanently repaired in a full time step. Specifically, the deterioration rate is a multiple of the repair rate, and 1 minus initial health value of each node is also a multiple of the repair rate. So under the above assumptions, the non-jumping sequence that targets the nodes in the decreasing order of the initial health values is optimal. So to give an idea of the proof of this result, we obtained the necessary and sufficient conditions for a non-jumping sequence to permanently repair X nodes. And then we showed that if a non-jumping sequence satisfies these conditions, then the sequence that targets the nodes in the decreasing order of the initial health values also satisfies these conditions. So theorem 1 said that non-jumping sequences are optimal, and theorem 2 says that the non-jumping sequence that targets the nodes in the decreasing order of the initial health values is optimal. So by both of these two results, the state feedback policy that targets the healthiest node at each time step is optimal. So now I revisit this example again that I showed before. Now we know that targeting the healthiest node at each time step is optimal under this scenario. And therefore, node A is the healthiest node and it is targeted first. And it is permanently repaired after the end of this first time step. And at this time, node B is the healthiest node that has not been permanently repaired yet. And therefore, it is targeted next. And it is permanently repaired in some time. But by that time, node C reaches the permanent failure state, and therefore it cannot be repaired. And thus, two nodes are permanently repaired in this scenario. And this is the optimal solution. Now I consider another case when the repair rate is sufficiently larger than the deterioration rate, which is given by this condition that delta increase is greater than n-1 times delta decrease. Then the optimal policy is to target the least healthy node at each time step. And to give an idea of the proof here, we first obtained the necessary and sufficient conditions for permanently repairing X nodes when the policy of targeting the least healthy node at each time step is followed. And then using these above conditions, we argued that this policy that targets the least healthy node at each time step is in fact optimal. And an implication of this result is that non-jumping policies might not be optimal when the repair rate is larger than the iteration rate. So to give an example, consider the scenario where we again have three nodes, A, B, and C with the same initial health values as before. But now the repair rate is equal to 0.3 and the deterioration rate is equal to 0.1. Now we know that targeting the least healthy node at each time step is optimal. So node C is the least healthy node at this time step, so it is targeted first. And by the end of this time step, node B becomes the least healthy node. Therefore, it is targeted next. And therefore, this policy of following the least of targeting the least healthy node at each time step is followed. And finally, all of these 3 nodes are permanently repaired. So we saw that for the case when the deterioration rate is larger than or equal to the repair rate, targeting the healthiest node at each time step is optimal. Whereas for the case when the repair rate is sufficiently larger than the deterioration rate, targeting the least healthy node at each time step is optimal. We also tackled a wide range of extensions for such problems. And to give an example, we considered the case when there is heterogeneity in the weights and the rates across nodes. And this is relevant. For instance, a local road might have less importance as compared to a national highway. And therefore, the weights that are assigned to these nodes can be different. And in the event when there is heterogeneity in the weights of the nodes, then the objective of the problem becomes to maximize the total weight of the nodes that are permanently repaired. Similarly, in the event when there is there can be heterogeneity in the rates across the nodes. For instance, a road that is affected by a minor flood might face less deterioration as compared to a road that is affected by a flash flood. And therefore, we considered heterogeneity in both of these weights and rates. And to give an example of a result, for the case when the repair rates are sufficiently larger than the deterioration rates, targeting the node with the least value of health minus the deterioration rate in a set Z at each time step is optimal. So I do not give the details of how this set Z is created here, but it can be efficiently created in polynomial time complexity using the parameters of the problem. We also considered another extensions where there are dependencies in the form of precedence constraints between these nodes. And that is also relevant. For instance, before repairing some sections of the electric water pumps, it might be required to repair some sections of the power systems. And we have some examples to show that the policies that are characterized to be optimal without precedence constraints need not be optimal when such constraints are present. And therefore, we focus our attention towards characterizing near optimal policies. And to give an example, the policy that targets the healthiest node at each time step while satisfying the precedence constraints permanently repairs at least half the nodes as an optimal policy when the deterioration rate is larger than or equal to the repair rate. Also, we considered an extension when there are multiple entities or repair agencies that charge heterogeneous costs for the repair that they do. And in such scenario, we considered the situation when there is a central authority that allocates these nodes to the entities, and it has a budget beta for paying to the entities for the repair that they do. And the objective of the central authority is to allocate the nodes to the entities in such a way that maximum number of total nodes are permanently repaired while satisfying the budget constraint. And therefore, we characterize optimal and near optimal policies for allocation of nodes to the entities for such cases. And just to give an example of what an allocation means, consider this scenario where we have 3 nodes and 2 entities on the right. So in this scenario, 2 nodes are allocated to entity 1 and node C is allocated to entity 2. So we provide optimal and near optimal policies for characterizing such allocations. And after such allocations, each entity targets the set of nodes that it is allocated. And finally, we also developed some heuristic policies that are motivated from these above policies for the cases where the optimal policies are not currently known. For example, when the repair rate is larger than the deterioration rate, but it is not sufficiently larger, we currently do not know what are the optimal policies, but heuristic policies like targeting the healthiest node or the least healthy node at each time step could still be used because we have proved them to be optimal for special cases of the problem. So now I'll conclude my work. We characterize optimal and near optimal policies for recovery of systems deteriorating after disasters. And these policies depend upon the relationship between the rates of deterioration and repair. And many future directions are possible for this work. For example, there can be stochasticity in the health values or other parameters like the deterioration rate, repair rates. Similarly, there can be some travel costs that are associated while traveling between these different nodes. Also, in our problem, we assume that the initial health values of the nodes are given, but estimating them could also be an interesting problem. And finally, I would like to acknowledge the support of NSF for our work. Thank you.